So now let's do this problem. Gradient descent with adaptive step size. In this problem, we'll consider the setting which will optimize our loss and make a parameter updates like this using gradient descent with adaptive step size. So eta is the step size and it's going to change over time over iterations. And for a given iteration t, this is going to be the learning rate eta for our gradient descent. Where alpha is a scaling parameter is bigger than 0. The first question asks us, says that f is a L-smooth function, then the following gradient descent update rule given above, we have to show that this holds for a sufficiently small value of alpha. Okay, so how we're going to do this? First, we know that f is L-smooth, right? What does this mean? What can we say about f? Well, we defined L-smoothness to be when this holds. T plus grad FW T. And that's great. And so this is what it means for a function to be L-smooth. Okay, so what do we do with this now? We have this gradient descent update that we can rewrite in this way, right? So basically, in this definition of L-smoothness, we want to introduce alpha, right? And in order to introduce alpha, we need to introduce eta, the learning rate, and the only terms that relate to eta are this guy and this guy, right? And we can rewrite this gradient descent update in this way, right? You just move the WT to the other side, and then you have this is equal to minus eta t grad f of WT. So this implies FWT plus 1 smaller than or equal to FWT plus grad FWT transpose. And then here we just replace with this guy minus, oops, eta t grad FWT. L over 2, and then again minus this, correct? Okay, did I make a mistake here? Perfect. So we have to put this in parentheses. And then, so now we want to introduce alpha. We want to replace, so the goal is going to be to replace this guy, eta of t, with its formula. But just one intermediary step before we do this. Let's clean this up a bit. Oops, sorry, this looks like this is WT plus 1, not WT plus 1. So it's a subscript t plus 1 here. Now we want to move this guy out and this guy out here also. So we have something cleaner to introduce alpha basically. It's just an intermediate step. You don't have to do it. So this is fairly straightforward. And then here we're going to have this. Right? But this guy is just equal to this. The norm square of the vector that results from taking the gradient of f of wt, right? You can think of this as, for any vector, this is equal to this, right? And so let's remove this and then put this here. Awesome. All right, now the last term. We want to remove this eta from the norm and put it outside, right? And this is a square norm, so we're gonna have to square minus eta. Minus eta t squared is plus eta t squared, right? Okay, perfect. So now let's replace eta t with this guy that we have here. You know what? I'm getting lazy, so let me do this. So the first part doesn't change. This doesn't change. This doesn't change. Only these guys change, right? So okay. So let's make some space here. Okay. First of all, let's remove the first eta t and then replace it with what it is, which is right. And then we can take this, which is eta t, duplicate it, square it, and replace it. Right? Did I miss a minus sign? No. Okay, so this is, I hope mean like moving stuff around is not confusing you. I'm just trying to save time and not rewrite everything because it's a long expression. But this is what we get basically from here to here by replacing with the formula of theta t. And now you immediately realize that there are some cancellations that can be done here. First of all, this cancels with this, and then this cancels with this. So we are left with this minus the norm grad ft plus L over 2 alpha squared. That's it. So a lot of people confuse my alphas and my twos. This is alpha. This is 2. This is alpha. So now this is great. We see this expression. And let's focus on, remember, what we want to prove is this, right? That this is true for sufficiently small alpha. Well, if we take the limit of this when alpha goes to 0 of this term, this is converges to f of t as alpha converges to 0, right? Note that alpha is always bigger than 0. And so if this converges to f of t, then this, for a small enough alpha, this holds. And that's the proof.